Hello students, welcome back. In the previous class we have studied about electromagnetic waves, that is chapter number 13. Now in today's class we will be starting with optics. Now according to the new syllabus, the chapter number 14 and 15 has been removed, so we are directly moving to chapter number 16, that is refraction of light at spherical surfaces. Now chapter 14 was for plane surface, so that is not there in the syllabus. Okay, so we are directly studying about refraction of light at spherical surface. Now there are two types of spherical surface, concave and convex. This you have studied from junior classes itself. Before studying about the spherical surfaces, the first topic which we are going to discuss is sign convention for measuring distance and length. That is the first topic of the chapter itself. So for that we will take a spherical surface, any spherical surface. Okay. So in order to obtain common formula for position and size of real and virtual images formed by convex and concave lenses, we have to adopt a common convention of giving signs, positive or either negative, to distances and lengths of the object and image and to the focal length of the lens. Different writers use different sign convention, but most of them prefer coordinate geometry sign convention. So we will the positive side of x, y axis, negative side of y and x axis, that is coordinate geometry sign convention. So similar sign convention is used in measuring the distance and length of a spherical surface. So we imagine this is a spherical surface, and a line passes through the center of the spherical surface. This line is known as principal axis. Okay, this line is known as principal axis. There is a spherical surface, and the center of the spherical surface, center of a single spherical surface is the pole. But if you consider a lens, the center of the lens will be optical center. Okay, there is a difference between pole and optical center. Pole is when we consider a spherical surface, a mirror. Okay, but optical center is for lens. So this point over here, we will write it as optical center O. The optical center of a lens is taken as the origin, and the principal axis of lens as x-axis. So this axis will be your x-axis. The line passing through the optical center and the perpendicular the principal axis is taken as y-axis. So this axis is taken as y-axis. All the distance are measured from the optical center along the principal axis and perpendicular as it follows. So first of all, distance measured to the right of the optical center along positive x-axis are taken as positive. So distance towards this side is taken as positive. And distance measured to the left of the optical center is taken as negative. Now distance measured upward from the optical center, upward is taken as positive, and downward is taken as negative. This you need to remember before starting the optics. And according to sign convention, the radius of curvature, okay, there are two things for convex mirror or lens. Okay, for convex surface, first one is radius of curvature and other one is focal length. Radius of curvature is also known as center of curvature. So for convex surface, radius of curvature and focal length are taken as positive. Okay, and for concave surface, radius of curvature or center of curvature and focal length is taken as negative. This is used for doing numericals and all, so you need to remember this part first of all. Okay, then only we can move forward with the chapter. So this is sign convention for measuring distances and length. Now, one of the most important topic from this chapter is refraction at a convex spherical surface. There is another topic similar to this one before this one, that is refraction at a concave spherical surface. That is not there in the syllabus. Only convex spherical surface is there in the syllabus. Okay, so in this figure, let S dash be a convex spherical surface separating a rarer medium, okay, rarer medium and a denser medium. So rarer medium of refractive index N1 and a denser medium of refractive index N2. Let P be the pole and C, if this is a spherical surface, if you make a circle over here, then the center of curvature lies somewhere. Yeah, this C is the center of curvature of the surface, and this distance is the, from pole to center of curvature, this distance is the radius of the spherical surface. So now let an object O be placed on the principal axis. Okay, we place an object O in the principal axis. An incident ray of light OA, okay, from this object, when light falls on this object, the light from this object falls on the spherical surface. So the incident ray from O, this is the object, falls on the spherical surface. Let this point be A. So OA is the incident ray. All these things, please note it down separately, okay? Such as R is the radius, OA is the incident ray, P is the pole, N1 is the refractive index of rarer medium, N2 is the refractive index of denser medium. Now, the light falls from object O to the point A. And from here, what happens? There will be refraction. Okay, there will be refraction. That means light will move from rarer medium to denser medium. So before that, let me draw the normal. Whenever we draw a normal to a curved surface, okay, if it is a plane surface, then it is very easy to draw a normal. Suppose if it is a plane surface, then when we draw a normal, we draw a straight line. But if it is a curved surface, then how do we draw a normal? We draw a normal from the radius. A line passing from the radius is the normal at this point. So in this case, how will you draw a normal? A line passing from the radius. Which part is the radius? This part is the radius. Center of curvature is the radius. So a line passing from the radius is the normal. So this line passing from this point is the normal. So let this point be N, that is the normal. Okay, this a very fade line is the normal. Now, whenever a ray of light passes from rarer medium to denser medium, then what happens? The light bends towards the normal. I hope you remember this. A light bends towards the normal. So now before that, angle of incidence is between incident ray and normal. There will be angle of incidence, that is I. So it will bend towards the normal. So it will bend towards the normal. Okay, so this angle over here is our angle of refraction. Let this point be I. That is where the image is formed. Okay. another incident ray OP, okay, another incident ray OP falls on the refracting surface normally. So another thing what we know is, if a ray of light falls normally on the surface making 90 degree, then it passes without deviating or without bending, it moves straight. So if a ray of light passes normally making 90 degree, it moves straight, it doesn't bend, it moves straight. So wherever this ray of light and this ray of light meet, okay, this light AI and this light that is OP, wherever they meet, that point will be the image I formed. And this image, which is after the refracting surfaces, that image will be a real image of O. This I is the real image of O. Now comes the most important, that is the derivation part. So first I'll tell you what to write down. First of all, write down the angle of incidence. Angle of incidence AON is equals to I. The angle of refraction AIC. Okay, AIC, angle of refraction over here is R. PO is this is the object distance, that is U. Object distance is U, but anything towards the left of the optical center or the pole is negative. Now PI is the image distance denoted by V. Anything towards the right is positive. And PC is equals to PC. This distance is the radius of curvature towards the right of the spherical surface is positive. Now this is according to the coordinate geometry sign convention. So now we will consider angle alpha, that is the angle between incident ray and the principal axis. This is angle gamma, angle between principal axis and the normal. This is angle beta, angle between principal axis and the refracted ray. Okay, so first is angle alpha, angle between principal axis and the incident ray. Angle gamma, angle between principal axis and the normal. Beta is the angle between principal axis and the refracted ray. So now we draw our normal from this point touching this principal axis, and this be the height h. Okay, h is the, let h be the height of the normal AM dropped from A on the principal axis. Okay, now in triangle COA, okay, in triangle CO and A, okay, in this triangle we have, in this bigger triangle, what we have is I is equals to, this angle I is equals to alpha plus gamma. That is because you can write down inside the bracket exterior angle is equals to sum of interior angles. Okay, due to that reason angle I becomes alpha plus gamma. Equation number 1. Again, in triangle CIA, okay, in triangle CIA, it is CIA, okay, in this triangle the same thing we will write angle gamma, exterior angle is equals to sum of interior angle, that is r plus beta. Okay, now from this same equation, r is equals to, if you take r other side and bring gamma this side, you can write down gamma minus beta, equation number 2. Okay, this is equation number 1, this is equation number 2. Now you can write down by Snails law, using Snails law. Now what does Snails law state? It states that sine of angle of incidence, or the ratio of sine of angle of incidence to the sine of angle of refraction, is equals to refractive index of medium 1, medium 2 by medium 1. That is the Snails law, which I have studied in class 10 also. I'll just write it down. That is sine I divided by sine r is equals to refractive index of medium 2 by refractive index of medium 1. Okay, this is Snails law. If you cross multiply this, what we can write is n1 sine I is equals to n2 sine r. Now there are few things we need to consider. That is, for a spherical surface of small aperture means a very thin spherical surface. Okay, there will be thin lens also. So we are considering very thin or very small aperture. The point A will be quite close to point P. Okay, the point A will be quite close to point P, and the angle I and R will be small. If this is very close, A and P are very close, then what happens? This angle I and R will also be very small. So if I and R are measured in terms of radian, okay, if it may not in place of degree but in terms of radian, then instead of sine I, we can write I, and instead of sine R, we can write R. Why? Because we are considering I and R to be very small, such that sine I is similar to I and sine R similar to R. Therefore this equation becomes n1, in place of sine I we can write I, in place of R, sine R, we can write R. Now substituting this in the values of I and R from equation number 1 and 2. Okay, we are now substituting this value of I and R in equation number 1 and 2. So n1, in place of I we are writing alpha plus gamma is equals to n2 gamma minus beta. Now we'll just multiply this. N1 alpha plus n1 gamma is equals to n2 alpha minus n2 beta. Now gamma and gamma, we will take one side, rest to the other side. That is n2 this side, n2 beta plus n1 alpha is equals to n2 gamma minus this side n1 gamma. We are bringing this gamma this side. Now n2 beta plus n1 alpha is equals to, if you take n gamma common, then it becomes n2 minus n1 gamma. Make this equation number 3. Now next thing what we are going to consider is, for a very small aperture, if the aperture is very small, the point M will be quite close to point P. So this is the point M. This M and P, they lie at the same place. They will be very close to each other. And alpha, beta and gamma will be so small that we may replace them by their tangent. So this alpha, beta and gamma will be very small. So we can write, in place of alpha, okay, in place of alpha we can write tan alpha. In place of beta we can write tan beta. In place of gamma we can write tan gamma. Now just refer to the diagram. Okay, I'll just read it out. Just refer to the diagram. Tan alpha. Okay, tan alpha. Alpha is equals to perpendicular by base. So perpendicular is AM, base is MO, or in place of MO we can write PO. AM by PO. That is our tan alpha. Now what is our AM? AM is the height h, PO is the object distance. Okay, so it will be h by object distance u, which will be minus u because it is left from the pole. Now tan beta. Similarly, tan beta, please refer to the diagram. I'll just write it down. Tan beta will be AM by PI. AM is h, PI is V. Now tan gamma is AM by MC. AM by PC, which is h by R. So I've got three different values of alpha, beta and gamma. Now substituting these values in equation number 3. So what we have is, our equation number 3 is N2 beta plus N1 alpha is equals to N2 minus N1 gamma. This is our equation number 3. Now putting the values of alpha, beta and gamma in this equation. So it becomes N2 beta is h by V plus N1 alpha is h by minus u is equals to N2 minus N1. Gamma is h by R. Okay, now if we take h common from this two side, we can write N2 by V minus N1 by u is equals to N2 minus N1 h by R. So h and h gets cancelled. Therefore, our equation becomes N2 by V minus N1 by u is equals to N2 minus N1 by R. Now this is what we are trying to derive. Okay, this is relation between object distance, image distance, refractive index and radius of curvature. Okay, this relation between N1, N2, V, U and R is very important. This is for any convex spherical surface, and even for concave spherical surface the formula is still the same. Okay, this is same for concave spherical surface as well. Now according to this formula, image distance, that is V, this does not depend upon the alpha. Okay, for that just refer to this diagram. Okay, from the final equation what we see is this V does not depend upon the alpha. Okay, this angle over here alpha. Hence all rays starting from O after refraction at the convex surface of small aperture will meet at the same point I, that is I is the real image of O. So wherever we keep the object, the image will be formed at I itself. Okay, it will be formed at I only. That is what this derivation proves. So this is for a single convex spherical surface. Now in the next class we will start lens. Lens you have already studied, but there are few things which you need to study in class 12 and are very important also. So we'll continue in the next class. This much for today. Thank you.